Welcome to our AP Chemistry discussion of solubility equilibrium. We're still in Chapter 10. It is what I would consider the second part of Chapter 10. We already did general equilibrium, and all those principles you applied in general equilibrium are still going to apply here. So if at any time you need to go back and review, that's why you have videos, so you can always go back and review whatever you feel you might have missed the first time. In solubility equilibrium, we're going to be looking at, as you can imagine, solubility. Okay, so what happens when we put an insoluble salt in some water? So in the picture here, I have some lead 2 iodide. We did this in pre-AP. You mix the two clear solutions and you got a yellow precipitate, and then you filtered the precipitate and saw it was a solid, and what went through the filter stayed clear because it was dissolved. But let's talk about that solid. It's sitting in water because those solutions were very dilute, so lots of water around it, sitting in water. What's happening to that insoluble salt? Maybe we should be asking this third question first. Okay, so while you're thinking of what's happening to the insoluble salt and what you would see, let's discuss what does it mean to be insoluble. To be insoluble, we were saying, at least in pre-AP, that it means it does not dissolve. So soluble, it does dissolve. Insoluble, it does not dissolve. How do we know it does not dissolve? Well, you kind of see it sitting at the bottom usually as a precipitate. Or at least that's what you think you see. So what happens to an insoluble salt when we add it to some water? It apparently does nothing. I mean, you'll agree, this is your experience. If we let that yellow solid sit there, nothing would occur. If you dump too much sugar into a glass of water, then you're going to see just a bunch of sugar sitting at the bottom, not dissolving. So you would say at that point in time you've passed the solubility, right? Well, that's probably a better picture of what's going on, because insoluble is a lie. Everything is soluble. All solids will dissolve. Now, there's truth in that they will all dissolve. Now here's the catch. Some of them dissolve just a very, 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 very tiny amount. So we're really not telling you what you have been noticing in your everyday life is wrong. What we're telling you is that you have to consider, even though you call it insoluble, a little bit does dissolve. A tiny bit. Itty bitty teeny tiny does actually dissolve. And that's that itty bitty teeny tiny amount that we're going to actually look at this chapter. Because there are certainly some very important chemical principles based on that little bitty teeny tiny bit that does dissolve. Okay, so here's my yellow lead 2 iodide sitting at the bottom of my beaker. Here's my water. The blue stuff is water because we all know water is blue, right? Anyway, what would it look like if you could see this happening? Well, you would see this. So check it out. Not only would you be seeing the lead iodide solid dissolving, it is a salt, so you're going to see it ionizing at the same time. Now in this picture that I'm representing, what you would see, okay, you would possibly see that if we could see it. My arrows are incorrect. Why are my arrows incorrect? Well, if you haven't guessed, and it's probably just a guess by now, the title of our unit is solubility equilibrium. And so we should really be using equilibrium arrows. The arrows should go both ways. Okay. We can let lead 2 iodide sit at the bottom of our beaker for a long time, and none of it seems to go away. But we do know a little bit is dissolving. And so how do we account for the little bit that dissolves if we say none of it actually goes away? Well, we must be setting up a situation where as some of it dissolves, some of it at the same rate undissolves. So my arrows really go both directions. I have dissolving occurring and undissolving occurring, precipitation occurring. and they're going to occur at equal rates if I see no change at the bottom. Wow, what could we call it if the reverse reaction is happening at the same rate as the forward reaction? Both rates are equal. Maybe this is why we call it equilibrium. Okay. So we really do, even with solids that don't look like they're dissolving, we set up an equilibrium. It probably is set up really quickly because it's a small amount that would dissolve at equilibrium. But that's all right. So let's talk about this. Equilibrium of an insoluble, or if you want, more truthful statement, a not very soluble salt, is coined or called or has the vocabulary of solubility product. Solubility being, how much dissolves. The product part you'll see in just a moment. So we call an equilibrium of an insoluble compound solubility product. Now let me contrast. I have a large beaker of water. I put a few grains of sugar in it. What do I expect to happen? I expect to come back and no sugar is sitting at the bottom. It has all dissolved. That would be a one-way arrow. That would be not a solubility product equilibrium. With lead to iodide, even though I put a few grains of lead to iodide in it, it would not really look like anything's happening no matter how long I give it. That's indication that we have reached the point where the arrows are both directions, and then it's in equilibrium. So not every solid would reach a solubility product equilibrium. Some solids are very, 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 very soluble and therefore would really be a one-sided arrow. Okay, so we're going to concentrate on not very soluble salts, ones that don't match your solubility rules that you've been told to memorize. Oh wait, do you need to go back and watch the video on solubility rules? If so, do so. But we call this KSP, equilibrium constant, specifically for solubility product. Do you need the SP? No. Is it nice to specify, hey, we're doing solubility product? Yes, it is nice. And very likely on the test in May, they will put the SP there. They don't want to trick you about what K you're trying to find. So they'll either say the word solubility product, equilibrium, or they'll write KSP, or maybe they'll say both. It's very possible. They don't want to trick you about what they want you to say. So here is my reaction for lead to iodide dissolving in water. I have taken out the water because there's water on this side and water on that side. It really cancels out the equation. If you want to leave the water in, that's fine, but it really complexes things when you really don't need, you don't need the water on both sides. It cancels. I'm not adding more water, so the amount of water doesn't change. When I go to write a KSP, we're going to write it like we used to. Products over reactants. So here's my products, and why is the I squared? Oh yeah, don't forget, still we're assuming slow step, one-step mechanism. So the coefficients are the exponents. So we write it as products over reactants. Oh, wait a minute. Now this is not unusual for KSP. KSPs usually do not have a fraction. We don't include the reactants. Why don't we include the reactants? We don't include the reactants because it's a solid. And what two things don't we include in any equilibrium? We don't include solids and we don't include pure liquids. We include things that are dissolved. We would include gases, but we don't include solids and pure liquids. Now, why don't we include them? Well, we're making the assumption that the amount of that particular item, solid or liquid, doesn't change significantly over the course of the reaction. And here, since lead to iodide is only very, 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 very tiny bit soluble, that's a very, very safe assumption. So it makes things a whole lot easier just to leave it out. And our general rule of do not include solids and do not include liquids in in any sort of equilibrium is a good way to continue. Okay, so I was squared again because this is the slow step, so our coefficients are the exponents. and we really should not have a denominator. The reactants are solids. I can't have a solubility product thing if I don't start with a solid or end with a solid, whichever way you want to view that. But there you go. Okay. Now, where we do a K, there's a Q. Okay, easy enough. Hopefully, last chapter you caught that K and Q are identical. When would you use Q? Okay, here's the important part. When would you use Q? If you don't know for a fact that you're at equilibrium. You can always write a Q under any conditions. You must know you are at equilibrium if you want to write a K. So we can write Q anytime. What's going to happen if Q is less than K? Okay, so you're like, well, didn't we just cover that last unit? Yes, absolutely, we did cover that last unit. Let's review because it's that important. Okay, so Q is less than K. If Q is less than K, we need more Q to equal K. To get a bigger numerical value for Q, I need the numerator to get bigger and the denominator to get smaller. So therefore, I need to shift to the right. The forward reaction will speed up faster than reverse reaction to get to K. And again, if you want to use our shortcut, always writing K on the left and Q on the right, boom, there's your arrow. Shift to the right. What would happen if Q is greater than K? If Q is greater than K, I have too much numerator, and not enough denominator. I want to make Q smaller to equal K. So I'm going to decrease the numerator, increase the denominator, products over reactants. That means we're going to shift to the left. And again, maybe double checking your thought process with our quick little mnemonic here. Yes. With K on the left, K is less than Q, our reaction will shift to the left. And what happens if Q is equal to K? You know that is, yes, you are at equilibrium. So if they don't state for a fact that you are at equilibrium in the question, you might want to find a Q first to see if you are or are not at equilibrium. Okay. So still for the same reaction. Let's simplify things. We could talk Q and K, but we know Le Chatelier's principle. So let's talk Le Chatelier's principle, which gives us the same ability to predict the change, just like Q less than K or Q greater than K, without even having to do any numbers. So that's why we really like Le Chatelier's principle. And to expect questions over Le Chatelier's principle on the test in May. I cannot imagine a test without questions over it. So according to Le Chatelier's principle, what would happen if you added NaI? And you're like, nope, no NaI, no NaI, no NaI, so it's going to do nothing. Well, okay, it's not necessarily a trick question. Sodium iodide. What do you know about anything starting with sodium? It's a very, very soluble salt. Any amount of it put into water, for our purposes anyway, any amount, will immediately, quickly, and completely ionize to sodium and iodide ions. Notice my one-way arrow. Okay, so within reason, any amount I put into my equations. Now check out what I have. I do have a match. So by adding sodium iodide, I am effectively adding iodide ions. I'm effectively changing the equilibrium. I'm messing with the amount of the iodide in the products. So what do we call this solution? Situation. Don't expect you to know. I'm just posing that for, let's talk about the vocabulary. We call this the common ion effect. Imagine that. We have an ion in common to both equations, and we call it the common ion effect. Okay, so what is that effect? Well, that's two questions down. What would happen to the value of K? If I'm adding in I, It doesn't change K, but it certainly now is not at equilibrium. I'd have to write a Q. And Q is, because I'm adding product in, Q is only going to be greater than K. So be very careful. What happens to the value of K? Nothing happened to the value of K if I add iodide. Only thing that can change the value of K is temperature change. But I am most certainly kicking it out of equilibrium. It's no longer at equilibrium. It's now a Q, and Q, because I'm adding product, is greater than K. Rewind that and listen to it again if you need to. Okay, so I've added product. Q is greater than K. What's going to happen? Let's do our little shortcut. CQ is greater than K. Oh, the reaction is going to shift to the left to get back to equilibrium. If the leftward reaction wins, I'm making more solid. I'm going to use up ions to make more solid for a while. So what's that do to the solubility of lead to iodide? It decreases it. How much? Well, we'll be able to figure out some other point in time. But I want you to catch that. By adding in an ion, it shifts the equation to the left. I'm making more reactant. It's going to decrease lead to iodide. So if I really want no lead to iodide to dissolve at all, ever, I could fill my beaker with a ton of iodide ion or a ton of lead ion, and it would shift that equilibrium, and to some point in time I could probably very close to 100% prevent anything from even dissolving. Okay, but all the time, the common ion effect is when you add a common ion, it will reduce the solubility of your slightly soluble salt, your not very soluble salt. Okay, tiny soluble salt decreases. Does it really change my solubility of sodium iodide? Because that's in there? No. This is a one-way arrow. It doesn't change that. Can't force it that way. This is a double-way arrow, so it can force it that way. Okay, so please notice the difference in the arrows. Please check out the common ion effect. We will practice this in class, but it's just an application of Le Chatelier's principle, so I hope you caught it. Okay, now let's actually prove this with some numbers. Okay, well, we would need to find the concentration of lead. So let's do that. Okay. So to find the concentration of lead at equilibrium, I have my reaction. Check that out. PbI2 solid is going to be in equilibrium with Pb2 plus aqueous and iodide minus aqueous. Okay, so there's my reaction. Okay, I should start out with some lead to iodide. How much lead to iodide am I starting out with? If you said, wait a minute, it's not given in the problem, you're exactly correct. It doesn't need to be. I'll prove to you in just a moment that we don't actually need to know how much we start with, but let's guess a number. So my shoe size is 9. So I'm starting with 9 molarity of lead to iodide. I have 0 and 0, and we could work in moles just as easily. I have 0 and 0 of that. Okay, the change. Some of this is going to leave, some of this is going to form, and twice the sum of that's going to form. Check out, I'm keeping my ratios going on. Okay, at equilibrium, 9 molarity minus x, x, and 2x. Now check out my KSP. Itty bitty teeny tiny, which we would expect for something that doesn't dissolve well. Because KSP is a products over reactants, and that means very little products, very little dissolving. So we expect KSPs to be very, very tiny. Not 0, not negative, but very, very tiny. Okay, so I'm going to assume that 9 molarity minus x is equivalent to 9 molarity because KSP is very small. Okay, let's get the point. Oh, sorry. Let's get the point for writing our KSP equation, our equilibrium constant expression. My products are lead 2 and iodide ion squared. My reactants are, oh, don't mess it up. Do not mess it up. There is no reactants listed because our reactants are solid. We don't include solids. We don't include pure liquids. I'm not going to include it. I don't want to lose my point. Okay, now let's plug. Plug and chug. KSP is equal to, wow, sorry, I don't know why that keeps doing that. PB is X, and I is 2X, and that needs to be squared. And PB, oh, I don't need that. Notice how I really need no information from that column at all, which is why we were not given an initial amount in the problem, because it really doesn't make a difference. Because I'm not giving an amount in that column, I didn't really even need to make an assumption to simplify, because I don't have anything to simplify if I don't need to worry about that column. So these are actually going to work a little faster than your regular K equilibrium constant expressions because there's no denominator. Now we are told this is equal to 9.8 times 10 to the minus 9. Okay. Now I need to have fun and solve for x. Do it one step at a time. I'm warning you, one step at a time. 2x squared is 4x squared. Did you get that? If you didn't get that, shame on you. 9.8 times 10 to the minus 9. And let's skip 2 slides ahead because we feel like it. Okay, so now when I combine these, I get, okay, I'm going to erase my assumption just so I have room. La la la. And while I have the eraser out, I can erase like this column here because it really doesn't matter. There we go. See how much simpler that makes things look? You're going to like KSP. They're going to be faster. They're going to be simpler. Until we talk about the common ion effect. Ooh, just made you scared, didn't I? It's not that big a deal. It's just one more step to everything that we already do. Anyway, okay, so I'm going to take this equation up here because I'm running out of room. So I now have 4x cubed equals 9.8 times 10 to the minus 9. Now before I grab my calculator, I'm just going to write it all out so I can type it all once into my calculator and be done. So 9.8 times 10 to the minus 9. I would divide that by 4 first. Then I would cube root everything, and I would get x. Okay, so now it's calculator fun time. Yay, everyone's favorite time of the day. Let's have some fun in our calculator. 9.8 e to the minus 9 divided by 4. And then I'm going to take that and raise it to the 1/3 exponent. Did you know that? Did you know that a cube root's 1/3? Square root's 1/2 exponent? So if that's easier for you to find in your calculator than trying to find the cube root, I'm sure your calculator has a cube root somewhere. Where it is, I have no idea. So just saying, hey, I'm going to raise it to the 1/3 power or raise it to the power of 0.333333, that is definitely good enough. Okay, so taking the cube root of that after I divide, do the division first, order of operations going on. Okay, I get x is 0.0013, and what in the world does that mean? Okay, x, which is the concentration of lead, means that's how much molarity of lead ion I have. Iodide ion is twice that amount, so that would tell me how much iodide I have. Now, I wasn't asked that. I was asked for the lead. So I'm going to have my answer. My official answer is 0.113 molarity. Okay. This is my final answer for what PB, the concentration of PB2 plus. Okay. So there's my final answer for this step. All right. Now we've added a common ion, and that will change things. But I want to pause here and let this sink in. All right. So you should be able to predict what adding a common ion does. We're about to prove it mathematically. But I'll see you back next time, and we will talk about the mathematics behind that.